You should be able to get most of the assignment done at this point. But today was probably going to be the last thing that we need to cover, which we started previewing on last week, Friday last week. I just need to make sure that the audio here is working, but well, yeah, there we go. So remember that we are live on YouTube and we are live on Piazza, so if you have any questions, go ahead and post there to either one. But in any case, let's see. So, hashing is yet another way that you can exploit hashing. Hashing itself is something completely different, but you can exploit hashing to store things in a data structure. Oops, I don't think I started this, so let me go ahead and give me 1 second. There we go. So, what does hashing mean? Oh, remember that like hash browns, you're taking something and you're cutting it up, right? Now remember, say from 235 or whatever, a function, right? A function maps a set onto a set. Right? The input set here, what do we call that thing? Right? If there's an x over here in this set over here that maps to some y over here, and this is the function f mapping x to y. What is this thing over here called? The set of all things that get mapped. Do you remember? Domain. And what is the set of all things that get mapped to? Range. That will be a subset of the things that actually get mapped, but in general it's a codomain. Or you're right in that it is a range. They don't necessarily have to be the same thing, right? If there are some things that don't get hit, right, then it's not on to, remember, right? So if this ends up being the range and this entire thing is the codomain, then and there's something left out over here, then it's not on to. That kind of detail is not necessary for this. Okay. So what does a hash function do? Generally, what we use is h, short for, hash, right? What the hash function is doing is it's taking the domain and chopping it up into a codomain. So here's the domain again, right? And intentionally, it makes it into a one-to-one, a non-one-to-one function. So actually, before we do that, let's remind ourselves what a one-to-one function is. If this is x1 and this is x2, what if they map to the same thing? Is that one-to-one or not? Yeah. It's not one-to-one. It's one-to-one when x1 maps to a distinct y1 and x2 maps to a distinct y2 for all x's. Okay? That is one-to-one. So what a hash function does is it's intentionally a non-one-to-one function. It takes this domain and splits it up into a hash, right? So we cut this up. Like this is our potato. Right? Or it looks more like an Easter egg right now, right? But what it's doing is it's cutting this domain up into pieces, into slices. Now the easiest hash function, the easiest way to think of this is h sub x is equal to something x mod m, right? Now, consider our domain over here to be all z, right? All integers. And our range over here, or our codomain then, is going to be 0, 1, 2, ... all the way up to m minus 1. So some things will get mapped to this first bucket. Other things will get mapped to these other buckets, right? This thing will get mapped over to this bucket or whatever. But basically, this is a hash function. It has hashed this domain into a bunch of congruence classes, if you want to look at it that way, right? Etc. Right? Yeah, go ahead.
Does it have to be a partition of the domain, or could it exclude and overlap?
Could it exclude?
Could there be? Does it have to be a partition of the domain where everything is in exactly one
It has to be in 1 because that's a function. If it's in 2, then you've got a function, one element maps to 2 things, and that's not a function. Right?
Yeah, does it? Okay, never mind.
If there are, now by necessity, by definition, there will be distinct elements over here that end up getting mapped to the same element over here. Right?
Is our codomain of the hash function a partition of the domain? Does it like partition it up into different parts and there's no overlap in between them?
Yes, because what would it mean that there is overlap? Then that would mean that 2 things get mapped to, yeah. Yes, I think so, because I don't know how to visualize it otherwise. I don't know what the implications for that would be if there's like this Venn diagram of, I mean, something gets mapped to that area or that area or that area,
Yeah.
right? But not one or a combination of those 3. So in essence, you do have 3 partitions here. You don't really have a Venn diagram of an intersection,
Okay.
right? But in any case, why is this good? Where have we seen these numbers before? 0 through m minus 1. Yeah.
In a like array list.
And the first word of that being the operative part, on array, right? So this allows us to take an element. We can start with an element x, what is an arbitrary object. And what we can do is we can take x and wash it through this hash function. This hash function, say, will give us a number, 0, or some number in z mod m, since we have used that before, right? Remember that that's going to be 0 through m minus 1. Oops. And what we'll do is we'll use this as an index to map to an array. Right? Excellent. Why is this nice? I have my object. I want to store it efficiently so that I can quickly find where it belongs, so I can put it there. And when I want to look it up again, I can quickly jump to that memory location, to that index, and retrieve the element that I wanted. All I need to do is have the element, right, and a repeatable hash function here, and I've got it, right? I've got the index at which it belongs. Arrays are extremely efficient, right? They're all memory contiguous. As long as you can jump to a particular memory location, you're good to go, right? So this idea offers us a way to have amortized constant time operations. If I only have to compute the hash function now, I can jump to that location where it is, right? That I can retrieve it. I can insert things by computing the hash function value, jumping to that memory that index, and putting it where it belongs, right? I can remove things too, right? All I need to do is find them and replace them. They're used all over the place, right? They're used in any hash-based data structure. If you're coming from Java, hash tables, hash sets, hash maps, right? Why do you think they're all called these things? Because there's a hash table sitting underneath the hood, okay? So let's go ahead, and now that I've given you the idea visually, let's go ahead and fill in the gaps there with some basic ideas. Again, the idea here is that elements are stored in a contiguous, fixed size array, right? It provides easy, free, random access to elements based on their index. Right? The actual index or location of each element, x, is determined by using a hash function, h sub x. Right? As long as the hash function is easy, and what I mean by easy, I mean efficient to compute, the basic operations of retrieve, retrieve, insert, or update or destroy are all efficient as well, right? Because all you do have to do to find the element is compute its hash and jump to that location. Generally, you use a key instead of the actual object, right? It is sufficient to consider integers, right? Now, why is this? For this, we're going to take a little bit of a detour. We're going to take a little bit of a detour into, say, Java and Python, right? So if I've got an object, say, like a student object here, a student object in Java here, I've got two strings, one of them first name, one of them last name. I've got an integer, which is an NUID, and I've got a double, which is a GPA. This is a full-fledged object. How do I take a student and map it to an integer x that I can then wash through a hash function? Right? How can I take an object and give a numerical representation of that object? Yeah, go ahead.
Probably makes sense to use the NUID since it's a unique identifier.
All right, you could use the NUID, right? And since it's unique, it's not necessary that everything gets mapped to unique elements because we've already, made the decision that we're using a hash function. So therefore, necessarily, it is not one-to-one. You could have NUID 1, 2, 3, 4 and NUID 4, 5, 6, 7, and they would map to the same hash value. That's okay, right? In fact, that's expected because you can't have an infinitely large hash table, right? If you had an infinitely large hash table, that means that you've got an infinite set here mapping to an infinite set, and can you store an infinite sized array? No. You want to keep your array actually small, right? Say, I don't know, 1,000 or something to start out with, right? So you could use just one of the aspects of it, right? By default, what does Java use? Do you know? Do you remember?
Is it like their space or like?
What do you mean space?
Location and memory.
Location and memory, exactly. Let me go ahead and run this. And you see that I've already created a student, me, and then here Jane. Built in from day one, over 25 years ago, it would be, over 26 years ago now, Java has always had this hashcode method attached to every single object. The default behavior here is to give you the Java virtual machine memory address, in which case it's just this number, this numerical representation here. If I run this over and over and over again, you'll see that I get the same hash function because these objects are loaded up in the same memory location each time I run the program. And I'll show it, I'll prove it to you. I'll go ahead and create another student object here. I'll call it AA, and print out its hashcode value, AA, right? And now, the first object that got stored got this 62248, et cetera, et cetera. Now, AA should have that hash code. Right? There we go. Now, A has B's hash code, right? And that's because it's all based on the memory location of the object when it gets loaded up, right? It doesn't matter, right? It's in memory, it's data. We don't care that it's student data. We don't care that it's two strings, an integer, and a double. We just use the memory location, and that's good enough for a hash function. It maps an object to an integer. All right, yeah?
What determines like the object memory? Because technically A is.
That's the Java virtual machine. That's
Okay.
its business,
Well,
right?
all right.
Let me go over here to student, and generally in Java, it's best practice to override the default values here, and to do that, all we're going to do is go over to where is it? Source, generate hash code and equals. When you do one, you generally want to do the other because, like I said, it's not going to be a one-to-one function. We could have Jane Smith and John Smith mapping to the same hash value, but they are distinct objects. So what happens, and that's perfectly fine because in the hash the hash table, that just means that they're stored in the same cell. Now to distinguish between them, between John and Jane, that's where the equals method comes in. Right? I'm going to go ahead and generate this, and you'll see that now that it's It's based on the entire state of the object, I should say. Right? I don't think that there's any rhyme or reason to the order that it generated it in, but whatever. Right? This is probably a convenience function that was added in Java 7, it looks like, right? Where you can just give these things and it'll take care of that for you. Here, two objects are equal if, well, this is equal to that. They're the same thing in memory location. Or if the other object is obviously null, we can't be null, and so it returns false. If they don't have the same class, then we return false. Otherwise, if the first name and the last name and the GPA and the NUID are all equal, then we say, yes, these in fact are the same thing. Okay? Python does something very similar. Where are we here? Here's Python. So let's go ahead and first of all, there's some weird things in Python. Let's go ahead and take, what do you think the hash code of an integer is? And by the way, how do you think you find a hash? It's hash. There you go. So I'm going to print out and I'm going to convert it to a string here because it is indeed an integer. Right? Hash takes any object, and in fact, takes any object or built-in thing and returns an integer value representing that thing. Okay? And let's run this. Python 3. What is it? Demo? There we go. 42. So what do you think the hash code value does to an integer? It just gives you back the integer. Not very creative, but a string is different. That's just some big number, right? It's just an integer. Yeah.
Does that mean that if we had both A equals 42 and B equals 42, that
they would have the same hash value, but that's okay because they can map to the same thing where it's not a one-to-one function, right? We'll understand that's called the collision, and we do need a way to deal with that when we use this as a data structure. That's coming up though. Right? What about 42.1, just so that it doesn't cast it to an integer, right? Some other big number, right? What about if I had a node? Hello there. Did I define my own hash value here? Nope. But it still works. Because like Java, it's built in.
It's different though.
Yep, it's different. Why? So here's some background on. I was also. I thought it was a groovy mystery too. So what I did is I went and did some digging, and apparently, it depends on the implementation too, whether or not it's Python or some other Python implementation. But in old school Python, apparently it was just the pure memory address, which was based on the ID method. So there's also this ID method, which is basically the equals method, ID, right? And originally it was based on the memory location as well. But in Python 3.3 or something like that, they introduced an element of randomization into it. And that's why you're seeing different numbers each and every single time. Right? If we use Python, here, let me go ahead and save this. If we use Python, just regular Python. Nope, it's still randomized there too. So at some point they introduced it to both of them. Okay. So it's built into pretty much any language because most languages recognize these hash-based data structures as essential, and so they built in these hash code values or these hash functions in order to enable that. Okay. How does it work? So, again, it's sufficient to consider integers. Why? Because generally you can map an object or its state to an integer, right? And then use that hash code to run it through a hash function that only works on integers. Right? So it's enough to consider integers here. Okay. What we'll do is our actual hash function will map And I'm going to copy this because I don't want to rewrite the entire LaTeX. There we go. We'll map Z to Z mod M, right? In other words, it'll take any integer, right? Again, you can take any object and map it to an integer. Once you've got that, we'll take any integer and we will map it to Z mod M. And again, that is just simply the numbers 0 through M minus 1. That allows us to use those as indices. The result is used as an index to map it to an actual array index, right? Thus, the array is of size M. Excellent. Okay. Unfortunately, I was worrying more about OBS here, so let me pull up an example. No, I want. There we go. So any questions so far? Yeah, go ahead.
So what it does is I don't know. I just don't see the use of mapping an object to an integer and then the integer to another integer.
Well, I want to, because
Is that what?
are you going to make let's do this one more time. Are you going to make an array of size -92233 blah 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 blah? Is that a valid index? We want to make sure that that's a valid index, right? And that's not it. So we need to run it through an actual hash function that gives us a valid index 0 through M, where M is the size of our table.
But
Okay.
if it's not like unique, then you could have multiple objects.
And that's a collision, and we will be dealing with that shortly here. Right? So let's just go ahead and go with this, this following hash function. Again, I'm going to operate on k for a key, right? And we'll go ahead and say that it's equal to 7k plus 13 mod m. Or, sorry, I actually need an m here. 8. Okay? Hopefully the broadcast is good. Let me just check. Okay, good. I'm just paranoid that since this is the first time I'm doing this, and by the way, my throughput here is through the roof with this new computer. Generally, I would only get like 2,500 KB per second, and so now it's like 9,000. So, yeah, and only 10% of the CPU, and it is whisper quiet. It's not even hot. You can hear that buzz. That's the fan of that thing up there. So nice, right? Anyway, so what I want to do is I want to map the following elements: 10, 16, 4, 13, and 86. Well, first of all, what am I mapping to? If my hash value, or if my hash function here is mod 8, then we're talking about Z mod 8, which is equal to 0 through 7. Right? So I actually have a hash table here of what size? 0, 1, 2, 3, 4, 5, 6, and 7. Of size 8 exactly. All right? So immediately you can see the problem here that you've been alluding to. Can I fit more than 8 things in this? Nope. So that's a problem that's a bridge. That's a problem whose bridge we'll cross here in a moment. Okay. Before we do that, though, let's go ahead and make sure that we can at least map the following elements. So what about 10? What is the hash value of 10 here? 7 times 10 plus 13 mod 8. So 70, 83, 83 mod 8 is going to be 3. So 10 gets mapped to 3 here. Okay?
Wait, so it's 83 mod 8?
Yeah, because it's 7 times 10 plus 13 mod 8. Well, okay, if you want parentheses, there you go. Usually the order of operations is that the mod is last.
Oh, okay.
Right. Otherwise, 13. If it was just 13 mod 8, that's just 5, and the mod goes away, right?
Yeah.
Useless. Anyway, h sub 16. Is it 5?
Okay, because it's 16 is a power of 8, so we have
Yep.
0 plus 5.
I think that you're right too. Yep, 16. So 16 gets mapped over here. All right? H sub 4. We'll do the full math there. 4 times 10 plus 13, mod 8. 40 plus 50, plus 13, that's 53. Mod 8 is what? Oh, so did I screw up? Oh, no, yeah, what am I doing? 10. 7. All right, there we go. 28 plus 13 is 41. 41 mod 8 is 1. So 4. We're good. Yep. H sub 13 is equal to 7 times 13 plus 13. And we'll do your trick again of taking out divisors of 8. Right? 7 times 13 plus 13 is 8 times 13. 8 mod 8 is going to be 0. So we're left with what? 0. Right? And 13 ends up going over here. Right? Now, take a look at the pattern. Right? Are they in order? No. Are they in order that order of the order that I put them in? No. Right? There's no ordering here. Right? We're just putting stuff in order to look them up. It's not like a card catalog at a library where I need to find this actual book. Okay, well, here's the Dewey Decimal number. And on the shelves, they're all ordered nicely so that you can go to section 600 and find what you're looking for, right? Instead, what the what the index card is telling you is exactly the location, not necessarily, it's like the entire library has been jumbled up and randomized. But it tells you exactly what shelf it's on, right? And the shelf and the fifth book from the left or something like that, right? It tells you the exact location. But just given the exact location, you can't find the next one, whatever that means, right? There are data structures, hash-based data structures, that maintain additional metadata so that you can also have an ordering if you want, right? But we won't get, we'll get there maybe later, okay? All right, what about 86? 86 is 7 times 86 plus 13 mod 8 is what? 7?
7, yeah.
86. There we go. Okay. So far, so good. One more. Let me go ahead and get rid of all this. Let's go ahead and go with H sub 100. If that's all I ever wanted to put into this table, we'd be fine, right? This would be 7 times 100 plus 13 mod 8, which is going to be what? $713, 1, I think. Anyway, it should be a collision somewhere. So 100 ends up going here. Can it? I could kick 4 out, right? We've got a new tenant for this home, right? Get out, right? And whoever the last person to claim that that cell, that index, is the person that gets to occupy that index, right? No, what we have here is something called a collision, right? Why? Because H sub 100 is equal to H sub 4. Oops. Again, what does that tell you about the function, the hash function itself? Two distinct elements mapped to the same thing. It is not one-to-one, right? Again, visualizing this. 100 and 4 are distinct, but they end up mapping both to 1. So it's not 1-to-1. And that's perfectly, I mean, that's expected, because you cannot have an infinite domain in a computer. You can't have an infinite domain mapping to an infinite domain because you can't store an infinite number of things. You want it to store it down into a small, manageable amount, manageably sized array. Right? But this does present a problem. How do we resolve these things? Right? And that's called collision resolution. Right? So if let's go ahead and go over here. Sorry, lost my spot. So collision resolutions. When two elements map to the same index, it is known as a collision. And by the way, collision detection, by the way, the hash functions that we've been talking about are for data structure hashing. They're for use in data structures. These are not cryptographic hash functions. You might have heard of, like of Bitcoin mining. Bitcoin mining uses, and Bitcoins in general use cryptographic hash functions. Cryptographic hash functions, you don't want collisions. You're going to necessarily have collisions, but you want them to be so improbable that the cryptography holds, right? And just as a digression here, since we are honors, right? You can think about this as passwords. Passwords. Right? If my password here is 1234, right? On an actual system, do you think that we store 1234 as your password? So that next time you log in, you enter 1234, and it checks, okay, 1234, yep, that string matches, access granted. Right? Is that how passwords actually work? Well, unfortunately, some of them, yes. And so if you ever have a website that you can recover your password and we'll send you your password, run, because that means that they're storing them plain text, unencrypted, okay? But that's not generally how they're stored. Instead, we send this through some hash function, right? Cryptographic hash function. Cryptographic hash function. Right? And this is my password here. And that gives me some hash. Right? For example, SHA, I don't know, let's go with SHA-1. Right? I wonder what the hash value of SHA-1 is. I don't have a web browser open, but we can. I'm sure that we can find SHA-1 online. There we go. By the way, SHA-1 is not a good cryptographic hash function as of a few years ago. You should not be using it, and I'll tell you why here in a moment. Let's hash that. So there's a hash value function, a hash value of the password 1234. 1234 is actually not the most common password. What do you think it is? Password. And there's the cryptographic hash of using SHA-1 on the password. Yeah, go ahead.
Would what also be a fairly common password?
What?
What is the password?
The password. You could have an entire passphrase there. Yeah, sure. Right. You can have an arbitrary string, and it maps to, it uses a cryptographic hash function, takes the string probably, takes the bit representation of it, treats that as an integer, and then runs it through a bunch of stuff. Right? Now, the reason that SHA-1 is no longer a good cryptographic hash function is because collisions have been found as of 5 years ago or so. Right? Why would that be a bad thing? Yeah. Password 1 and password 2 map to the same hash. Guess what? Instead of entering 1234, I can now enter in whatever collides with it and access granted. Now, that's not a showstopper. That's just a canary in the coal mine. Meaning that just given this hash here, could I go back and find out what password 1 or what password 2 was? Can I? What is it called? What is it called when you take a function and reverse it? Inverse. And there's no inverse. Why? It would map to two things. It's not one-to-one. For an inverse to exist, it has to be both onto and one-to-one. Right? It has to be bijective. And by its very nature, it's not invertible at all. But you're still not sunk. As long as you find another password here that maps to the same hash, you can still circumvent the system. Now that's extremely difficult, right? That's what Bitcoin mining is all about. Finding a hash, a value that maps to a certain hash in order to mine your coin, right? That's a very simplified view of it, but finding these things is a great amount of work. But the mere fact that you found a collision means that your days are numbered. Right? Eventually, somebody will find what's called a pre-image attack. Right? That you can find any old value here that maps to the same value over here. Right? Right? So collisions aren't the end of a cryptographic hash function, but they are a strong indication that you should stop using them. Right? In fact, when this was discovered, it was pointed out that, well, it breaks a lot of stuff already. Right? For example, the example that was given was, here's a PDF. Now here's a second PDF that has the same hash value. And then it was committed to GitHub. And then it was updated to the second PDF that had the exact same hash value. There was a collision, and because it used at the time SHA-1 to determine commit numbers and stuff like that, then there was you can't have two distinct commits with the same identity, right? And if you committed, I think that the experiment was if you committed both of those files, or if you committed one of the files and then the other file, it would completely screw up your entire Git history, right? Because of this collision. So the solution was to switch over to another cryptographic hash function for which no collisions had yet been found, right? SHA-256, SHA-2, and now we're on SHA-3. It's not widely adopted yet. Check. Yeah?
So why would you want this? Like,
why would you want this for passwords?
well, I mean, what's the use of, like, you said hash tables or hashing is very intentionally, like, not one-to-one.
Right.
Why do we want that if it leads to stuff like this?
Well, no, this is a good thing, right? Just given my hash value. If I break into a system and steal all the hash codes, you're not owned yet, right? Pwned, or whatever you want to call it, right?
Okay.
I can't find this second, without a lot of work, I can't find this and break into the system using this alternate password, right? And not only that, but just given the hash, it is mathematically impossible to reverse it because there is no inverse, right?
I think also these are cryptographic hash functions, which are different applications.
Yeah, it's definitely a different application.
Oh,
Right.
okay. So it's different.
But they're all hash functions in that they hash up an infinite domain into a small or a large codomain. Large for cryptographic, small for data structures.
Okay.
Sorry.
So is that why, like, in hash maps, you can use, like, the key to find the value, but not
Exactly.
necessarily find the value to get the key?
Yep, exactly. The hash maps don't work both ways. Now you can go ahead and implement a hash map that, and it's not in the standard Java, but you can have a hash map where it goes back and forth. And then that's called a bidirectional function, right? A bijection, right? And then that's under the hood, you're still using hash values. It's just that you're using two of them, one to go one direction and a distinct hash function probably to go to the second direction. It's no different than maintaining two hash maps with values, keys, and then keys and values reversed. All right, so go back over here. All right. So how do we resolve these collisions with respect to data structures? If a collision occurs, you can simply map it to a second value, a secondary location. Right? And the easiest way of doing this is called linear probing. Right? Go to the next adjacent cell until you find a free one, or unavailable one. That is empty one. Right? You could also use quadratic probing. Use a quadratic function to probe for another location, probing, linear probing, quadratic probing index. All right? You could use a secondary hash function. You can use a secondary hash function for collisions, etc. So again, we'll only look at linear probing, what it might look like here, okay? So let's go back over here to our work table here. So I hit a collision here with h of 100, right? H of 100 needs to go in here, but it's full, okay? So what could I do? I could probe it, right? So this one's not available, right? Let's go to the next one. And is it available too?
Yes.
Yep. So let's go ahead and put 100 in there. Excellent. Problem solved, right? Well, let's continue. 8 sub 108. And it's just 8 more. So mod 8, what do you think is going to happen? It's also going to be 1. So we end up coming over here. We see that it's already taken. So we probe again. Okay. That's already taken. So probe again. That's already taken. Probe again. And we finally found something that's free. So put it there. One more. 116. Again, what do you think the hash value is going to be? 1 by design. And so we end up, again, looking at 1, probing over, full. Oh, finally, we found something that fits. Let's go one more. And what happens then? An infinite loop, or we find, it's full. The hash table is full. We can no longer fit anything into it. All right, well, if an array is full, what's one solution if you still want to cram some more stuff in there? Okay. Can I just do that willy-nilly to the end of an array?
Well, sure.
No.
An array, a regular old array, not an array list. A regular old array is always of a fixed size.
Yeah,
Right.
sadness.
Okay. So the first table that I tried was too small, right? If you want to fit more than 8 things in this, you need a table that is more than size 8. So what I will do is I will rehash. Right? Create a new table larger than the old. So in this case, let's go ahead and go from 8, we'll go double the size. Z mod 8, we'll go up to Z mod 16. Right? And exactly how you do this is all an implementation detail. Do you double the size? Do you triple the size? Do you go from size X to X plus some factor, X plus 100, right? Are you increasing this linearly or geometrically or whatever, right? And that's all an implementation detail. All that, in fact, that all can be parameterized so that you could have an implementation that adjusts how it is growing depending on how much it has to grow, right? And you could get really, really sophisticated for that. But what's the problem here now? I had my old hash table, which was of size 8. Here's the old values, and here's the new thing that I want to add to it. Right? So I've now created a new table of size 16. But everything is still over in this other table over here. I didn't just add on to the end, by the way. Again, you can't do that with an array. Instead, I created a brand new array here. And I need to do that because my hash function has changed. Whatever it was before, what was it before? 7 times k plus 13 mod 8. Now it's different. Now it's mod 16. Right? And that will give me completely different hash values for every single value. Right? Even if I keep the same coefficients here. Changing the modulus changes the function. So what do I have to do to every single element? I have to rehash them all. In other words, for each x in the old table, recompute the new hash value, new, of x, and insert into the new table. Right? But at least I've solved my problem of it got full, right? What do you think the complexity of this is? Given that the computing the hash value, the hash function, that's my elementary operation, right? Inserting something into the new table, well, that's just jumping to the index and putting it right there. That's constant too. So these two things are going to be order 1. But how many times am I doing it? However many were in the original table. This is going to be order n. Right? Now, is that good? That's like a regular old linked list or a regular old array list, depending on what your operations are. Right? We don't want that. We just came from the world of balanced binary search trees where everything was order log n. And now, are we going to accept an exponential slowdown? Yeah.
Well, we only have to do it 1 out of n times.
Yeah. Rehashing is infrequent. So, is expensive, but infrequent. There we go. Nice edit. Rehashing is extremely expensive. It's going to be order n, but it is infrequent. Right? If you only ever do it, say, once every millionth operation, right? Or once every, say, 1 over nth operation, then it might not cost you that much. Right? Why? Because if it only costs you n, but you're doing it infrequently, 1 over n times, guess what? That's amortized constant time. Right? So, again, let's think about this in terms of a graph. Okay? So here's my cost, and this is a very hand-wavy graph, by the way. And here's the lifetime. Here's time. Right? Here's the lifetime of the table. Now, just putting stuff in, searching for stuff, that's extremely efficient. It's order 1. All you have to do is compute the hash value, and then you jump to the location and you're done. Right? Now, you might have some probing, and we'll talk about that next time. But ultimately, that's going to be cheap. Right? So the cost is cheap until it starts to fill up. And you have more and more, oops, that's not what I wanted. Shut that off. Right? I don't know how to shut that off. So I'll just lift my pencil. Right? So it gets more and more expensive as the hash table fills up. Right? Because now you've got a lot of collisions. And you've got a lot of probing to do. And if you start deleting things, you have what's called a dirty bit that you have to take into account that we'll talk about next time. So once it gets too expensive, you pay for that high cost, right? So it costs you a lot. Like this is just a hand wavy cost measure here. But then immediately the cost goes right back down, right? And then it's very, very cheap, very, very cheap, very, very cheap until it starts to fill up again, right? So the table is full, right? The table is full. And so, again, you rehash. Rehash, rehash. Right? And you have this kind of spikes and troughs, etc. Right? Now, take an average over the lifetime. Right? In other words, sum up the cost of all these values here, and then divide it by the time, and it ends up being some constant. Right? Now, that constant is going to be greater than a lot of, say, these operations, right? But it is going to be nowhere near the order n operations that you pay infrequently, right? So over the lifetime of the data structure, when you amortize that, right, the amortized cost, then it looks to be constant, right? And that's why we call it amortized constant time, right? Because it looks constant. It's not constant because, of course, it is changing. And if you were to map this stuff out, it does change. And every so often, but infrequently, you pay a great price to rehash everything. But over the lifetime of the data structure, it's actually quite cheap. And this is why anytime you ask yourself, say computer science 2, what kind of data structure should I use? Immediately, without even knowing anything about the problem, some sort of a hash table, right? That's the go-to answer because they are always so cheap. All right, looks like our stream did well today. And I'm going to go ahead and transition.